video that you made yesterday?
Yeah.
I was trying to watch it, and there was no video of any writing.
Are you kidding?
Yeah, I was having a tough. I thought you were gonna like visualize it right now. I was like freaking out.
So which one didn't have any, but there were two videos, neither of them had anything?
No,
It's just-
they were you.
It was just a face cam.
It didn't have what was on my screen.
So not, I thought I sent you an email like 30 minutes after you sent that because I
I
started.
don't know. I didn't see, if so, it got buried like underneath the screen
that's
right
fine,
away and I
yeah.
haven't gotten there. Oh, that's terrible. All right, well, in which case I'll need to do some things from last time. All right. That is such a bummer. No, I never want my picture on the video. I don't want that at all.
Well, it's going on YouTube now.
Oh no, we did the brachistochrone. You didn't even get that. That's a good problem. All right. All right. Okay, well, that'll be interesting then. Thank you so much. All right, so I'll probably just delete those two and how terrible. I'm gonna go and get the notes that I made from my lecture yesterday and walk you through them, instead of rewrite them, even though you were just. I didn't realize that there was no.
You don't want to redo the video?
I could rewrite them, but it would take, redo the whole, you're saying redo the whole lecture?
Yeah, just go on this plan, start chapter 7 today, and then
I think that it would make sense for me to go through those because you need that background to build on, so, yeah, on that.
Any plans for break? No.
what do you?
Just work on projects. And what? Here, I'll just show you. Mhm.
19? Or
No,
did you
that's
like build
wood.
that?
That's wood. Yeah, that's 100% wood.
Made that entirely.
Yeah. Like,
That's really cool.
yeah, this is just a mock-up for like hardware placement, just to kind of get an idea of what it's gonna look like on the product. I'm just doing the body. I ordered that. I don't feel competent enough.
Oh, yeah.
Because that's gotta be like,
Spot on.
yeah,
Yeah.
perfect. And it's really easy to like, because there's a lot of like curvature. So you've got like radius for the fretboard, which is the radius is based off of like the curvature of a circle of a specific size. So it could be anywhere from like 7.5 inch radius all the way up to like 16 inch radius, and then you've got compound radius, and that's just
Yeah, but it's really complicated.
yeah, like it's beyond me, at least at my current skill level. And I'd rather not like work on it for like 3 months and not have anything to show for it and
Yeah.
watching it. So like,
How long
and,
did that take?
I mean that's probably about 8 hours worth of work. Not much at all.
Really?
Yeah, because I mean the wood itself is it's a burl, so it just naturally looks like that.
Oh, it does?
Yeah. And
That's an interesting note.
yeah, so how burls are produced is generally fungus gets into the tree And as a defense mechanism, it grows around where the fungus is, trying to contain it, to keep it from spreading. And it causes all these patterns, these irregularities to pop up. So rolls are typically more brittle. And so this is just like a cord-wrench thick piece glued onto a inch and a half, quarter-inch and a half thick piece of mahogany. And so the mahogany is where most of the tone comes from, and this is just purely just because it's cool looking.
Yeah, aesthetics.
Yeah, it's just cool looking.
Oh, that's really cool.
I'm hoping to get it pretty much ready for like clear coat and finishing.
What do I do before that?
I'm gonna run out holes here, neck pocket here, lots and lots and lots of sanding, hole filling. The mahogany on the outside is going to be painted black, so I'm going to do a few coats of black on that and get that ready for clear, get everything sanded down really, really, really smooth, and get it ready for clear coat. And clear coat, use a lacquer, typically like a lacquer finish, and so like you want to do anywhere from like 10 to 20 coats of clear. And then you can't use it for like a month because you have to let the lacquer set and harden.
It takes that long?
For it to completely harden, yeah. So I mean, it'll be hard to the touch after a couple hours. But even after like 15 coats, you can do one coat 15 minutes apart from a second coat. So every 15 minutes, and it'll be hard to the touch, but it's going to be susceptible to like scuffing and scratching and stuff like that. So you want to let it harden for a long period of time.
It's a process, yeah.
So, but I mean, I'll have everything put together, like dry, before finishing, just to make sure everything fits in real nice and everything. And so I'll get to play it before it's like, before the week's over.
Oh, really?
Yeah.
Wow. Yeah, I can't believe it. Just hard. We're really interesting.
What's going on?
What's going on is technology is mad. All right. That's not it. If my lecture equipment had just worked before, we wouldn't have. Was there?
Oh yeah, that is really low.
Huh?
That is really low. The
Yeah, I
little
can't.
end piece.
I mean, and the thing is, it's so tight, you can't use your right hand. So it's not good. All right, so, one more issue here. Okay, all right. So let's get going. I'm gonna pick up from, sort of a while ago, because the online lectures that I recorded for you did not have any visual aids. All right, so we need to really understand where this Euler-Lagrange equation comes from. All right, and then we're also going to use it today in mechanics, in which case it's called just the Lagrange equations. All right, so what we have here is we have an integral of a function that has a dependent variable y and an independent variable x, and it's integrated over x. And I want to find the path along which that function would have, in the case that it was location as a function of time instead of y as a function of x, it would be what we would call the motion. We want to find that function for which this integrand is minimized. And so in order to do that, I'm going to have to sort of make up a variable that I can consider a derivative along. All right, so just to remind you, so then what I do is instead of thinking of I sort of say that the path that will do the minimizing I will call y as a function of x, where y is lowercase. And another path, an arbitrary path, can be expressed as that path plus another function of x, where that function of x is eta, and it must be equal to 0 at x1 and x2, since it actually is the path that goes from point 1 to point 2. Next, we redefine capital Y and with one more level of sophistication to say, I'm going to let this y as a function of x, which is this arbitrary path, be equal to the desired path, which provides the minimum integral, plus that eta function times a constant alpha, where alpha can be anything. That's a real number. It can be -1. Where we want it is where it is 0, and it can be 1, and it can go do that. So we will want to do that. And so that's what we have, all right? So in this case, our capital Y of x will be equal to our lowercase y of x when alpha is 0. So far so good, because I know you've seen that before. All right, now, none of that is new, but it still has been a while, so we need to review it. So then we make a substitution for our new capital Y's, and wherever we see a capital Y, we substitute the form that we had for it, and then we notice that this y plus alpha eta is a variable of its own, as is y prime plus alpha eta prime. It's another variable of its own, and then we have this, our independent variable x. So if I want to know how this varies with alpha, this is a function in 3 variables. So I can write it as a sum of 3 terms, where I have df dA times dA d alpha, plus df dB times dB d alpha, plus df dx times dx d alpha. X doesn't depend on alpha, which is why dx d alpha is automatically 0. All right? Okay. Then we make these substitutions, because I'm obviously exploring the case where alpha was small, in which case A, where alpha becomes infinitesimally small, in which case A can be substituted with y. But dA d alpha will still be equal to eta in this functional form. All right, so that's what I have there. Similarly, for the second term, I have df dy prime, well, df dB times dB d eta d alpha, in which case I can make that substitution for b with y prime, because I'm exploring this case where alpha is small, but I still have dB d alpha is eta prime. Okay, you guys all right? That's where we got that. That's a very important expression. Now, I think this is where I picked up last time. Is that right? I think this is where the math became fresh.
Mm-hmm.
So this is an okay form, but this is not the form that I want. So I did a substitution here. So I say recall, which is it's fine if you don't remember it, but maybe once in your life you heard about integration by parts, or maybe once in your life you're working with somebody who solved a problem with integration by parts, and you're like, wow, you're a genius, because that happens too. It's really, really useful when it is useful. And so integration by parts, the point of that is that wherever you have the product of the function u and v, evaluated from initial to final, that's equal to the integral from initial to final of u dv plus the integral from initial to final of v du. All right? That's what integration by parts means. So it's a way to evaluate, if you had one of these integrals that you want to think about, you could express it in terms of the other 2 terms, and maybe it would be simplified. So that's what we're going to try to do in this case. So we're going to imagine the integral from initial to final of u dv, and that's equal to the product of uv, evaluated from initial to final, minus the integral from initial to final of v du. And then, so this is really what I mean by when I say use integration by parts to see if you can't make the integral easier or more understandable. So in our expression, I want that to be the thing that I can evaluate through integration by parts. So I am going to let, because I want this to be u dv and I want it to be equal to that, I'm going to let v be eta, and I'm going to let u be df dy prime. In which case, dv dx will be eta prime, which means that dv will be eta prime dx, because I'm also going to need to make some substitutions here. Again, just continuing with the calculus necessary to make the substitution I'd like to make. In that case, also du dx is the derivative with respect to x of partial of f with respect to y prime. So that du is equal to the derivative with respect to x of the partial of f with respect to y prime times dx. Now I'm ready to make a substitution for this term here, okay, using integration by parts. So using this boxed equation. I'm going to make my substitution with these variables down below. And what I get is that the integral from x1 to x2 of df dy partial of f with respect to y prime eta prime dx, which is what I had in my previous integrand that I didn't want anymore. That is equal to eta times df dy prime evaluated from x1 to x2. That is 0 because eta at x2 must be equal to 0 and eta x1 had to be equal to 0. That's how we define eta. All right. Minus this next term, which is going to be now our v du. So it's eta times the derivative with respect to x of the partial of f with respect to y prime dx. That's what we wanted, all right? So wherever I saw that before, I'm going to make this substitution now. So where I had that before, which is here, this term, I'm going to make this substitution now. All right, so now I have the derivative of that integral with respect to alpha will be 0, meaning that s will be minimized, the integral will be minimized. In the case of the integral from x1 to x2 of eta as a function of x times the quantity partial of f with respect to y minus the derivative with respect to f with derivative with respect to x of the partial of f with respect to y prime dx. Now, in order for this to generally be equal to 0, since eta is not generally 0, it must be, and regardless of that, you know, of all these different, without loss of generality, it must be that this guy here within the square brackets must be equal to 0 for that condition to hold. All right. So our new minimizing s condition becomes that guy in the square brackets is equal to 0. And that guy in the square brackets is the partial of f with respect to y, and I just went ahead and clarified that my variables of f are y and y prime and x. Minus the derivative with respect to x of the partial of f with respect to y prime must be equal to 0. That's called the Euler-Lagrange equation. Although you see it more often in this form. Hopefully you recognize that that is the same thing, all right? That is also called the Euler-Lagrange equation. This is probably the more general form. Instead of having their difference being equal to 0, you have them equal to each other. All right. Now, in terms of applying that, we first applied it to that shortest path problem, which was the first thing that we started this chapter with, where we expressed the shortest path from location 1 to location 2. And we had it as dx squared plus dy squared, although we could make a substitution for dy squared, that it was dy dx quantity squared times dx squared. And so that left us with this dy dx quantity squared, which we're calling y prime squared. Okay? I could go back to the figure, but if you're all right with that, let's keep going. So this is one of those cases where I have an integral, which I want to be minimized, and the argument of that integral, the integrand, is this function. All right? Now, that integral will be minimized when df dy is equal to the derivative with respect to x of df dy prime. All right? So we start thinking about, well, what's df dy? Well, remember, this is a partial. Y doesn't appear there, so clearly that's 0. df dy prime is actually a pretty simple derivative to take, 1/2 the quantity 1 plus y prime squared, quantity to the negative 1/2 times 2y prime. Okay, so my Euler-Lagrange equation I've written in that first form where it still has the difference is equal to 0. df dy minus the derivative with respect to x of df dy prime equals 0 leaves, so I plug in my 0 for df dy minus the derivative with respect to x of this object from here must be equal to 0, which tells you that this object here must be equal to a constant, just some stupid number, 2, 4, whatever. And And therefore y prime, I just need to get it alone on one side of the equal sign, and I get that it's plus or minus y prime squared is equal to plus or minus a constant, or is equal to a constant, therefore y prime must be equal to plus or minus a constant. It must be equal to a constant value, therefore the shortest path between 2 points was indeed a straight line. All right? Logan, you look like, are you okay? All right. Okay. All right, so the next thing that we need to keep in mind is we have these variables. X was our independent variable, y was our dependent variable, y prime is the derivative of our dependent with respect to our independent variable. All right? So that if I decided to talk about motion, say one-dimensional motion, I would define the x-axis as the line along which the motion occurs. My dependent variable would be location, would be x. My independent variable would be t. And my derivative of my dependent with respect to my independent would be x prime, which would be called probably x dot. Okay? In this next example, I am not doing a mechanics problem. I'm doing another problem, but in this problem, it's easiest to choose my independent variable is y, and my dependent variable is x, and solve for x as a function of y to find a path. That's just as good as knowing y as a function of x, so it's just fine. And in this case, my derivative is derivative of x with respect to y, okay? So I wanted to take you through that example. It's called the brachistochrone, good word. We've got these 2 points, P1 is higher than P2. What shape do we build the track for a frictionless roller coaster such that a car released from rest at P1 can reach P2 in the least amount of time? All right, so the thing that I need to do is write an expression for the time, which will be in the form of an integral, and I'm going to need to think about when the derivative of that is respect to 0, that's the minimum, which means that the argument to that integral would have to be a minimum, which leads us to being able to apply the Euler-Lagrange equation to that function, which is the argument of the integral. And that's what I'm going to do. Are you guys following that? Okay. So I need to write an expression for the time it takes to get from P1 to P2. All right. Well, and I'm going to make it as a sum of infinitesimal bits, also known as an integral, and the bit of the path has a length that is the square root of dx squared plus dy squared. And we will also notice that ds must be equal to the velocity at the speed at that time times dt in magnitude. All right. So the energy at some time must be equal to the energy that it had at point 1. So the energy at any point along this path must be equal to the energy it had at point 1, because I have a conservation of energy here. The car's wheels are rolling without friction on the axles. They're rolling without slipping. So, okay, I get to neglect all that. So energy will be conserved in this case. So E1, the energy at some location will be 1/2 mv squared minus mgy, because I'm taking this P1 and I'm making it the origin of my coordinate system, and it's at rest at P1. So that will be equal to 1/2 mv initial squared, which is 0 because it started from rest, plus negative mgy initial, which was 0, so this whole right side here is 0. And I can solve for the velocity at all locations y as the square root of 2gy. That's why we made y our independent variable, because we have this nice relationship. All right, so the time that it takes to go from point 1 to point 2 is the integral from 1 to 2 of dt, which is the integral from 1 to 2 of ds over v. And I make my substitution for v, as I get ds over 2 square root of 2gy. And remembering that ds was equal to dx squared plus dy squared, where I want my independent variable to be dy now, so I express dx as dx dy times dy. So for dx squared, I get dx dy quantity squared times dy, which gives me x prime squared plus 1 quantity square rooted times dy for ds. I make that substitution here, and I've got what I need. All right, and I go ahead and pull out my 1 over square root of g out front. 1 over square root of 2g out front. So now, this integral will be minimized when this function is the solution to the Lagrange equation. So here I've written out the Euler-Lagrange equation, and so I've got, in this case, I had to make a change of variables, because this is the original form where my function was a function of y, y prime, and x. Now my function is a function of x, x prime, and y. So wherever I see a y, I'm going to replace it with an x. Wherever I see a y prime, I'm going to replace it with an x prime. Wherever I saw an x, I'm going to replace it with a y. Okay? All right. So that is done here. All right, so now I'm about ready. So I've got my function of x prime and y, which is x prime squared plus 1 quantity to the 1/2 times y to the minus 1/2. So now comes the fun part. df dx. Clearly f does not, this is a partial, f has no x in it, so that's going to be a 0, minus the derivative with respect to y of partial with respect to x prime of this object. So that gives me a 1/2 x prime squared plus 1 quantity to the negative 1/2, just through the chain rule, times 2 x prime times that y to the minus 1/2. And that must be equal to 0, which means that this guy here, for which the derivative, of which I'm taking the derivative, must be equal to a constant. We call that constant 1 over the square root of 2a. That's a choice that your author made. Fine. Okay. So then I do just some algebra counseling these twos, for instance, and I get an expression that x prime squared is equal to y times the quantity x prime squared plus 1 over 2a. So I got x prime all alone on one side, and I squared both sides to get rid of that square root. All right. You can reproduce that on your own time if you'd like. I'm still trying to get x squared all alone on one side of the equal sign, and I get x squared all alone here. It's equal to y over 2a minus y. X prime is not what I wanted. I wanted x as a function of y. So I need to remember that that is equal to dx dy. So if I want to know x, I will go ahead and, I've got an expression for x prime here, I'll multiply both sides by dy, and I'll get on the left-hand side dx is equal to this object times dy on the right-hand side, and I'll integrate from initial to some arbitrary location later, and my integral of dx will give me x minus 0, because I started off at the origin, and my integral of the right-hand side will give me the integral from 0 to y of the square root of y over 2a minus y times dy. It's a messy function, so I put it into Wolfram alpha, and I got a solution, which is x as a function of y. So I know my answer. All right, so I come back here. Yeah, it doesn't look that way, it doesn't look that way there, but if I rotate it like this, that's what my answer is this function here. All right? So the point of this is that you can do something now that you've never been able to do before. And that's it. And you won't feel that way until you actually do it. And I don't know, there's going to be a problem like that on the next homework assignment. I've got one already in there written, but I've got kind of a cool one about light going through honey. I kind of like to, but all right. Anyway, so that's how we can do it, to find these stationary solutions, meaning the value of a function for which a particular type of integrand is either minimum or maximum. So the thing, though, is that sometimes you get these solutions and you don't know if they are the minimum or the maximum. All that you really know that a Legendre equation is giving you is that it's a stationary solution. All right? You have to conceptually think about whether it's the minimum or maximum. I didn't show you this, but it's not a difficult thing to do. You can find the shortest path between 2 points along the surface of the Earth, because in that case, your two variables, since r is constant, are just theta and phi. You can make one of them independent and the other one dependent. You could do theta, theta prime, phi. And you could find for which theta is a function of phi, the line from point 1 to point 2 will be the shortest line. The thing is that you'll get two solutions. One of which, and both of which will be a great circle, meaning that they will be a portion of a circle that includes the center of the Earth as the center of the circle. So this is supposed to be drawn such that that's the center of the Earth, and this whole thing makes a center, it's a circle around it. So you'll get one portion, which will be one solution, and that's called the geodesic, the shortest path. But that will also describe the longest possible path. So that same great circle will also include the longest path. So you kind of have to think conceptually about which stationary solution you're getting from that minimum to maximum and which one corresponds to it. In this case, you got two of them. All right. So one more thing that we have to say before we can start what we wanted to do today. Yes?
So you wouldn't be able to take like the double, the double derivative, find out if it's a maximum or a minimum?
Well, that's not something that the Legendre equation is going to do for you.
Okay.
You, in theory, could go back and apply that, but that's, the Legendre equation itself isn't going to give that to you. And you can go back and apply it mathematically and get the double derivative, or you can just, since most of these are going to be physical applications, you can usually figure it out conceptually. Okay, sometimes we're going to have two things that are a function of time. This, or a function of a single thing. Obviously, you see where I'm going with this. You might have x that's a function of time and y that's a function of time, and you want to know two-dimensional motion, maybe, that type of thing. So in that case, we've got one thing that's a function of u, another thing that's a function of u, and u is our independent variable. X prime would be dx du, and y prime would be dy du. In that case, you can imagine wanting to find a function, an integrand of a function that depends on both of those things. In the next chapter, that function is going to be called the Lagrangian, and we're going to have a lot of fun with it. In that case, all that you get is you get these two Euler-Lagrange equations. So where you used to have one Euler-Lagrange equation, now you'll have one for each of the variables in terms of the independent variable. That's where I want to pick up. So, okay, get that out of the way. All right, so today I want to spend a little bit of time talking about the Lagrange equations. So this is still the very last section of chapter 6, although it really should be the first section of chapter 7. So I'm going to sort of say that it's, let's say it's part of chapter 7. Okay. So from last time, we had, if we had some integral s, that was the integral from u1 to u2 of a function that depended on, say, x of u, y of u, dx du, also known as x prime, dy du, known as y prime, and u, where u is our independent variable, integrated over du. If I wanted to find, well, I guess I'll just be clear about it. I will wind up with two Euler-Lagrange equations, but I want to show you where they come from. Because I have x, which is a function of u. And again, I'm using this same idea that x is the function of u that I want. And I know this is a little unclear, but this is what your author uses, so I want to be clear that I want it, for which that integral is minimized or maximized, plus alpha times another function of u, which is represented by the letter c, squiggle. All right. Similarly, y will be a function of u, and it will be the desired function of u plus another variable, I think beta makes sense, times eta of u. All right. And so what I need, the condition I need to meet for x to be my wanted value is that ds d alpha is equal to 0. Similarly, the condition I'll want to meet so that I get my y function that is wanted is that ds d beta, and by the way, those are partials, will be 0. All right? And that condition is going to be, again, I'm not going to do the whole integration by parts substitution, but that leads to, on this side, df dx minus derivative with respect to u of df dx prime. And you'll have to look to figure out when they're partials and when they're fulls. Must be equal to 0 for this condition to hold. Try the math that we just showed you 10 minutes ago. Similarly, by that exact same math, I will get that df dy minus du of partial of f with respect to y prime must be equal to 0. So that's why we get these two Euler-Lagrange equations, which are, we're going to go ahead and start writing them in the more customary form. df dx equals d du, df dx prime, and df dy equals d du of df dy prime. All right, and these are the Euler-Lagrange equations. I'm going to keep that on the EL equations. In the case that I go ahead and make the substitution for t in place of u, and where x will represent a component of the location, and y will represent another component of a general location, in that special case, these equations get to be called the Lagrange equations. Okay. So what will happen then, so I'll just say in mechanics, which is what we're here to study, these can be, x and y can be any coordinates. Generally we'll call them q1, q2, and so on, where q1 might be the x component and q2 might be the y component of a location, all right? So we will use things like that to replace x and y, and so on. In that case, x prime, y prime, I'm doing this a little bit backwards. We'll say x and y will become q1 and q2. X prime, y prime will become x dot, y dot, which we will call q1 dot and q2 dot. And so on if there's a z component, or maybe more than one particle. All right? And obviously u, which is the independent variable, is going to become time, because that's what we want to find is motion. Location is a function of time. All right. So the actual motion, in the actual component of location as a function of time for our system will be expressed as q1 as a function of time and q2 as a function of time. In this case, let's just say we're just dealing with a two-dimensional problem. A particle moving in a plane, something like that. All right. But it will be the values for which a certain integral of a certain function will be minimized. So this will be the function of time for each of these, which minimizes a certain integral. You're probably saying, which one? And that's exactly what you should be saying, because that's what we're going to express for you. So in terms of the idea, though, that we have these general coordinates, they can be anything. So one example is, let's say that you have a system like that you've never seen before. So that this is an angle theta 1, and here's just a sort of massless piece of glue that connects that pendulum to another thing, and then here's your actual mass of m sitting here. So this angle here is theta 2. You can always describe the orientation of the system with theta 1 and theta 2. All right, they're two variables. And let's say you want to actually know the location of the mass as a function of time. You can express that in terms of theta 1 and theta 2. So in that case, what you would have is you would have, this is by the way called the double pendulum. And we're going to solve it. In this case, you have these variables. You have theta 1, which will be a function of time. You have theta 2, which will be a function of time. You got your theta 1 dot, you got your theta 2 dot, and you've got time. All right? So I will say, I've got this integral that will be minimized when a certain function is the actual path of this mass, meaning theta 1, mass's location is a function of theta 1 and theta 2. So it'll be the integral from t1 to t2 of some function of theta 1, theta 2, theta 1 dot, theta 2 dot, and t, dt. All right, so that's, and in that case, you're probably saying, what is that function? That function is going to have a special name. It's going to be called the Lagrangian function. I'll give you the form of that in just a moment. And once you have that function, we can rewrite this integral. And whenever you have an integral of that special function, which is called the Lagrangian function, we call that the action integral. All right? And so it's the integral from t1 to t2 of the Lagrangian, which we write with a script L, not a capital L because that is angular momentum. All right? And this will be minimized for the actual theta 1 and theta 2 as a function of time that describes the motion, the actual motion of the mass. So in that case, that means that this will be minimized for the following condition. d theta 1 equals d dt of dl d theta 1 dot. And dl d theta 2 is equal to d dt dl d theta 2 dot. All right, so if I could find the theta 1 and theta 2 that solve these two equations, that will be the actual, those two will determine the actual motion of my mass. And those two will be sufficient to describe the actual location of my mass. All right, as a function of time. So the next thing that we have to think about is that somehow this solution for the motion must contain all the same information as Newton's second. That's going to be the key that we need to figure out what the form of the Lagrangian is. All right, so we need that special function for the Lagrangian that will have that information in it. Okay, so now that was sort of the end of chapter 6. Now we're actually starting chapter 7. And I wanted to be clear here that I was wrong about, in the previous lecture, I remember being kind of surprised about the time of Lagrange. Lagrange lived from 1736 to 1813, so he is many generations after Newton, and that makes a lot more sense. Okay, but anyway, we are going to use these Lagrangian equations of motion in mechanics for some really great problems. Whenever a problem is best understood using a specialized coordinate system, so maybe it's highly constrained, like motion along the surface of a sphere, an object sliding along the surface of a sphere, stuff like that. So wherever it's sort of a constraint is a big deal, it's great to use Lagrangians because you can, Lagrangians don't care what Q1 and Q2 were. You can just use the coordinates that are necessary. And then the other constraining forces that aren't along those directions, you don't even have to know them. So you don't have to solve for a normal force when something's sliding along the surface. And so, yeah, as you will see. So it's just kind of great because it takes everything that doesn't matter to the motion and that you're probably not interested in anyway and removes it from the problem. So, and any time that unusual coordinates are necessary, you definitely want to use this instead of Newton's second. So what we are going to do for right now in order to figure out the form of a Lagrangian is we are going to let all non-constraining forces be 0. And we're just doing that for now. Oh, that's not what I wanted to say. we're going to let all non-constraint forces be conservative. That makes more sense. Meaning they do zero work. That's all we need in order to get the form of Lagrange. All right, so what that means is that friction does no work unless it's static friction, because the static friction never acts through distance. So like if there's an object that's rolling, there's obviously friction, but as long as it's rolling without slipping, there is no work done by it. So we will say all non-conservative forces, do zero work. I don't know what I'm going to say. We'll say conservative. No, we'll say be conservative. We'll stick with that. I know, me too. All right. I'm in a hurry. It's not good. It's not been a good week. All right. So, all right. So friction cannot do any work, and it can be there. It just has to be static friction. All right. So let's talk about Lagrange's equations. We're going to start with unconstrained motion to get the form of Lagrange. That says unconstrained. All right. So I'm going to ask you to consider a particle moving unconstrained in 3 dimensions, subject to a conservative force. That means there's no walls. And that conservative force, I'm going to represent it by F of R. Okay. In that case, kinetic energy, we're going to represent with a capital T, is 1/2 mv squared, which is 1/2 m times x dot squared plus y dot squared plus z dot squared. Okay. Also, potential energy, which we'll represent with the letter U, will just be a function of location. And that'll be the potential energy associated with that conservative force. Okay. Then, it must be that the Lagrangian is equal to T minus U. That must be the case. And we should notice here also that our Lagrangian is equal to that function, which is a function of, in this case, x, y, z, x dot, y dot, z dot, and t. So in this case, we would say that we have something called 3 degrees of freedom, 3 coordinates, directions along which the object is free to change its location. Okay, so why must this be the case? Because dl, partial of L with respect to x, is equal to, let's see, partial with respect to x, acting on this object. So t has no x dependence, so it'll be acting on negative u, x, y, and z. And that will give me minus u dx, partial of u with respect to x, also known as, and the partial of the Lagrangian with respect to x dot is equal to the partial with respect to x dot of, well, the only thing that has an x dot in it is 1/2 x dot squared plus y dot squared plus z dot squared. It's just a partial, so I get 1/2 times m times 2 x dot, 2's cancel, I get mx dot, which is the x component of momentum. And in that case, my Euler-Lagrange equation tells me that that condition holds when dl dx is equal to d dt, dl dx dot, also known as f sub x is equal to time rate of change of p sub x. And here's where we see that the Euler-Lagrange equation can contain the same information as Newton's second law. And we did this in the special case of rectangular coordinates where it was the easiest thing to see. We'll do it for polar coordinates in a moment. All right. So this tells us that the Lagrangian, this form, plus the Lagrange equation, we're now just going to call it the Lagrange equation because we have that u is t, all right, in these locations. So it's okay to notice this is also just a Lagrange equation now. Gives us a path for that condition that minimizes action that will be equal to the path that one would get by solving Newton's second law. They are equivalent. All right. So, I can't get these things to stay. All right. Let me write out, I need to write out Hamilton's principle as well here, stay. So those words that I just said, let me just go ahead and sort of restate them in Hamilton's way, which is that the action, which is equal to the integral of a special function called the Lagrangian, integrated over time from t1 to t2. So that is called the action integral. Is stationary for the path that the particle follows, where that path is the solution to Newton's second law. Just to be clear, for x, t, y of t, for instance, path that the particle follows, or that actual path is the solution to Newton's second law. So it is indeed equivalent information, but it is mathematically a different process that is sometimes, especially in the case of non-rectangular coordinates, really a lot easier to do. All right. So this statement here is called Hamilton's principle. And Hamilton was an Irish guy. He lived in the 1800s, 1805 to 1865. All right, and this will hold in any coordinate system. It didn't have to be rectangular, such as x and y. It could have held in r theta phi. It holds in any coordinate system, or even something that's even more arbitrary than that. Now, your chapter 7 starts with a really cool quote from Hamilton as well. I don't know if you guys read that. Did you guys read that quote? Read that quote. And then go look for everything else Hamilton ever wrote, because he's like a very dramatic and quote-worthy person. So you really have what it takes now to think about some really cool problems, but you're going to have to think about them over the break because we didn't have time to do them in class today. Check out these problems. These are problems that are often the last comprehensive qualifier thing that our department gave. So this is the one from last January. And you are in a position now where you can actually, did everybody get one? I got an empty page in the middle too. Did everybody get one? Okay. We are going to be in a position where we get to solve these on our next day. Unfortunately, you have to wait 10 days for it, but have a good break. I'll see you when you come back. was awful. This is a bad week. Good on you for surviving it. All right, see you guys later.